Hello, everyone. I'm Wundagi, so I'm a lecturer in hybrid AI at the University of Edinburgh. So I'm honored to chair the next session, which will be about using large language models in automatic sentence coding. So for the first talk in this session, we are going to have Stephan Schulz from DHBW talking about the e-prover.
Okay, thank you. I've been collaborating with Joseph for 20 years, more or less. And so this is very much complementary to his talk in both style. I have a lot more images. And he talked about the past, I'm talking about the future. And he talked mostly about machine learning, and I'm talking about also machine learning, but also other things. So this will be, I think, a good fit to what we already know. So let's talk about where we are. This is how I see the math ecosystem approximately now. We have something called the literature, and that is chiseled into stone tablets or written with blood on vellum, sometimes printed in ink on papyrus, things like that. And then there's people working on the literature, trying to increase it and improve it and find out new results. And we have some small individual islands of happiness where people have formalized small parts of math and are working sometimes with computer assistants on these small islands. And now, about 2 years ago, 3 years ago, some kind of gobbling monster appeared called ChatGPT, and we have what's now called the age of artificial intelligence. And here's our happy little state of the world approximately right now. Now you put this monster onto this playground, and the view, I think, of the AI gurus is that they'll now just gobble up all the literature and take over the world. Yeah, I don't agree this is going to happen. I think that's quite unlikely. Because large language models, we've all played with them probably, they are amazing, but they're also amazingly stupid. And what they are good at is processing language. They're very good at language tasks, like summarize the text, translate a text, but they have certain weaknesses. So my claim is, you always say mathematics is the language of science. I think that's a nice metaphor, but it's not true. Mathematics is not a language. And claiming it is about the same mistake they made back in the 1950s when they invented COBOL, because the hard thing about programming is a language. No, it's not. The hard thing of programming is sorting concepts in your brain to put them together in a coherent way. And I think the same thing happens in math. We have, of course, a mathematical language, or rather we have a family of mathematical languages, different dialects, both based on human languages and mathematical field. But math isn't a language. I think at its core, in the abstract, math really is the study of new structures and their properties. And the important thing here is new structures, not new texts, not new language. I think you all know how LLMs work. Basically, it's text completion on steroids. They do learn, and we're talking about LLMs in the pure sense, not about systems that are now called LLMs that are Franken monsters with all kinds of things stuck on. But pure LLMs, they learn conditional probabilities of how to continue a token sequence in the most likely way, and then they semi-randomly pick among the likely options to produce the next token and just repeat this process over and over again. But that means they really learn on token sequences, on language. They don't learn abstract theory. They can't learn abstract reasoning, at least not in this model. And they can't do calculations. And for the simple fact that for any token, you only have a finite amount of computation in your neural network, which is giant but finite. So you can't do arbitrary complex computations in a finite amount of neural activity. There's a couple of sources for this. There's a paper just published by Jeff Sutcliffe called A Chat with Bard, where he is discussing with Bard, one of the LLMs, the earlier ones, about a logic puzzle. And Bard solves that puzzle perfectly well. But then you do an isomorph transformation of the puzzle into different terms. So instead of talking on Agatha, who's rich, and the butler who may or may not have murdered her, you talk about a completely different field. I don't remember what Jeff did. Something like you have a football player on a field with certain rules, and the AI completely failed because it doesn't understand the structure of the problem. It doesn't do the reasoning. It only has seen this puzzle and similar ones in the past, and it just regurgitates, which it has seen to provide what's called a solution. There's a couple of papers that has come out. This one is from the Apple guys. They use LLMs to solve mathematical puzzles, and again, works fairly well. But then they just add nonsense information. So they add irrelevant facts to the problem. And because the LLM doesn't understand the structure of the problem, it only looks at sequences of words, adding extra words leads it to really different trajectories, and the success rate goes down wildly. Where any human would see, this doesn't have anything to do with the problem, it's just there to confuse me. And there's another paper where they have actually proven, or claim they have proven, I haven't checked the proof in detail, that LLMs will always hallucinate. So that is they can always be made to produce nonsensical content that's not based in reality or in their sources. It's unavoidable. And I think at the heart, what LLMs do, because they learn conditional probabilities, they just stay within what they know. They are reproductive. They don't create new stuff, except nonsense stuff. But otherwise, they basically just return what's put into them. And you can get, now there's many safeguards built in, but if you look at the basic models, you could prompt them and they would give you back complete texts of novels and stuff like that. If you put in long enough nonsense strings, they would randomly reproduce arbitrary pieces of input. So these are great tools, but they are just tools, and they can't reason in the sense we understand reasoning. They're only doing word completion. And that means they can't do new mathematics because they don't understand the structure they're talking about. They only understand the words, the sequences of words. So if I believe that LLMs alone are not the future of mathematics, what is? And let's go back a step. At the moment, all the hype is on LLMs. But of course, LLMs are just one application of deep learning. And deep learning is just one example of using neural networks. And neural networks are just one small part of machine learning. And machine learning is just one small thing about AI. And it's by far not the most important one. The most important one, of course, is logic and deduction. But let's put them on equal levels. Just one is in the forefront now, the other one is not so important at the moment. So what I see in the future is something like this. We will hopefully eventually get a formal unified database of formalized math, where everything that's in the literature will eventually be encoded in a number of compatible formats, ideally in a format based, in a family of formats based on a common base. So I think formal math has to be in a formal logical language, probably some version of higher order logic at the moment, but Stephen Obura will probably disagree and say it has to be abstraction logic. I have no strong opinion on that, but I think it's something that's a bit beyond first order logic, but not very much. Sorry? Maybe. Possibly, I don't disagree. But I know too little about types to be able to make a strong commitment to that claim. So I expect this to be structured in a reasonable way. You will have a query language, you will be able to isolate parts relevant to your domain. And I think as soon as one of the different approaches will be big enough and has good enough tooling, it will be like a snowball effect. All the other ones will eventually move in just because you have that amazing, increasingly complex infrastructure and existing basis to work on. I mean, at the moment, Lean has a lot of inertia, in a positive way, impetus, but I don't know if that's going to hold on, but it's one idea. So what do we do with this thing? Well, the first thing is we will probably work quite a long time to formalize mathematics into formal logic. And as you can see, I've got, does this work? Oh, it works, yes. You've got teams of humans and robots, and of course, the exciting thing here is robots doing it on their own. So full auto-formalization, I think one important goal, if we ever achieve something close to that, it will give us a huge boost to really put science and math on a more formal, more reliable footing. And of course, the more important, the more exciting thing is not formalizing old stuff, but inventing new stuff. I think I mentioned yesterday that I think by 2050, 2060, we may have the theory of everything, quantum relativity, with the support of formalized mathematics. I'm not sure, but I think. Another field, quantum cryptology, and also put in here something I only put robots on, that's useful blockchains. I put robots on this because I think it's hopeless and I don't want to disappoint humans. But who knows? Maybe they'll find something like that. So, in order to be able to achieve this, we will need hybrid systems. Interactive theorem provers, I think, kind of on a trajectory to become the user interface for mathematicians into formal logic. Automatic theorem provers are already used as hammers in ITPs to boost productivity, and they will only become better. We also have problems with consistency of large knowledge bases, and ATPs can be used to automatically detect inconsistencies and help fix them. Of course, we will need machine learning. Joseph talked a lot about improving proof search using machine learning, so I don't have to now. And I think LLMs will also have a place, namely in translating between different formalisms and non-formalisms, but not as the tool to do mathematics. So I see, of course, because I'm an ATP guy, automated theorem proving at the hub of the ecosystem. And I've got a couple of things here. I won't talk about all of them. Also, I've only got 4 minutes left. But these, oops, sorry. Yeah, but some of this I want to discuss quickly. The first thing I will mention, consistency checking. I think Joseph and I and Adam Pease and who else was on that? There was a fourth person. Jeff Sutcliffe, yes, had a paper on detecting inconsistencies in large knowledge bases automatically. And we found that Sumo had quite a lot of bugs. We found that OpenPsych had quite a lot of bugs. We found that Misa had no detectable bugs at all, but Joseph thankfully put some in, and we found those as well. So there's some, it's not that we failed to find the bugs, or maybe we failed to find bugs, but if we put in some bugs, we detected them. So just checking an existing knowledge base for bugs is important, but more important, if we go to this big unified knowledge base, of course, there will be different corpora coming together, and that always increases the chance of inconsistency. Maybe if I say times, I mean manipulation of natural numbers. If you say times, you mean concatenation of strings. And if the same symbol is used, probably you get some interesting new mathematical results you don't expect and maybe don't want. So I call this merge consistency. And that's probably going to be a big field if you try to unify mathematics in a formal sense. Also, Adam Pease has worked on Sumo, and he has basically created a workflow where every new bit of information he puts into the database goes through the Theorem prover to maintain its consistency. That is a big advantage of quality control. It really helps keeping the facts straight. Okay. Second thing, Joseph's big topic, I think. I've been trying to work on this since 1993, and since 1997 with E. But E became so successful that people always asked me for other features. And so I kept adding features, and other people, thankfully, took up the mantle and did machine learning. And sometimes they involved me, and sometimes I provided them with some additional things. But I think this is an immensely productive field. We've had quite some success, but it's a lot harder than we originally thought. And I think we are only just now getting to the power of hardware and size of data sets we need to make real progress. And I look back 25 years when I started back then, I tried to learn from like 10 proofs with a total of 1,000 steps. And I had some successes, but it's really amazing what we can do now, how easy it now is to generate thousands of proofs, millions of proofs, and learn from them. Last thing, which I found very exciting, and what originally Bruno Buchberger put me on when I did a short postdoc at Risk Linz. He wanted to replace himself. That was still his task in life. He wanted to make himself superfluous. And of course, one thing we want to do is to find new math. And there's different approaches of how to do that. If you have an existing theory, most of our theorem provers nowadays are generating theorem provers. They just enumerate some families of consequences. And then you can check if some of them are interesting. So you need a criteria for interestingness, which in my experience can be based on the relationship between proof size and formula size. A small formula with a big proof is likely to be interesting. Things like that. But there are other ways. Another way is, I think, what Moa worked on is just use different techniques, either symbolic or LLM-based, to come up with conjectures. But I remember the LLM-based conjectures were kind of boring. It always said, it's a binary symbol, maybe it's commutative, maybe it's associative, but it's, yeah, so. And you can, of course, iterate this process as long as you like. If you have some interesting facts, add them to your axiom base, continue, build more levels, higher levels on top of that until you have something amazing. And of course, we have an amazing amount of computational power that's only used to warm the planet and for nothing useful otherwise. So that's one way we can maybe use that hidden resource. Okay, conclusion. I think, and I've for a long time maintained, that automated reasoning and machine learning are the two core complementary concepts of AI. You need to be able to reason and you need to be able to learn if you want to be intelligent. I think LLMs are overhyped, but that does not mean they're useless. In fact, they're very, very useful, but they can't do everything. And I think in math, they can do less than is currently believed, unless you boost them by adding different modules, of course. But I think there are lots of other machine learning-based techniques that will be very, very useful. Okay, time's up. But one thing I learned is put the most important thing you want people to remember last. So please remember, Kate this year will be in Stuttgart at DHBW. They are very excited. They don't know what they are in for. So please do all come, make it a great success, so that they learn that conferences can be fun and they do more interesting conferences at Stuttgart. Okay, thank you. Questions?
Thank you. Can you hear me? Yeah.
Yes.
So quite interesting, and I honestly I do find I agree with your perspective on most of what you said. There was one thing you were saying in the beginning that it's not that I disagree, but I think you're too sure about it, which is that maths isn't language, and I feel like that is a very tricky philosophical question that I don't think we have an answer for. So I wonder, could you elaborate on why you're so sure that maths isn't language?
I said math is not a language.
But a lot of people think that, it's not that thing, that a lot of people wonder if reasoning, you said it's the concepts in your mind and so on and so forth, but that could be considered a language. It's not natural language, but it might be a language. So
Yeah.
So
I think I understand what you're asking, stating. I don't do most of my reasoning in inner monologue. I do some of it in inner monologue, especially when formalizing things, writing them down. But a lot of things I just stare at very, 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 very hard, then go to bed, then get on my bicycle, then ride down the street in dangerous traffic, and suddenly I know the solution.
Okay.
Hopefully not when the light turns red, but sometimes. But I understand that, yeah, some parts of thinking are linguistic. But then if you look at things like Chomsky's grammars, they are much more general than what LLMs do. LLMs are basically working regular languages, like sequences of tokens. They don't abstract, they don't go to more abstract concepts. And that's why I think it's they're failing here.
Okay. Thank you.
Yeah, we may have time for just another question.
Deep pass.
Hi, thanks for your talk. In the beginning, you mentioned that, language models cannot, or they only reproduce data, but then at the same time, we speak about hallucinations. Isn't that just, well, to me, that seems like it's kind of as a counter argument for that, even if most hallucinations are obviously wrong. I think one could argue that people do that in the same way that they something like that.
Okay, I mean, there's an ex-KCD comic that I should have put in here about machine learning, where they have, here's my machine learning system. It's a pile of linear algebra. I put the answers coming on the other end, and well, I keep stirring the heap until. So yeah, I agree that one way to creativity is like making random decisions and then looking at the quality of the output. But if you, that's only to a very small degree what LLMs do. They most look at existing text and then reproduce sequences of tokens they've seen before. That's why I say they are essentially reproductive, not they are totally reproductive, but the creativity is very limited. It's not like a quantum leap thing. It's just like they can produce random garbage and sometimes the garbage is gold. But it's an accident, it's not an inherent feature of the system.
Thanks.
At least that's my opinion. Again, strong on opinions here. Okay,
I think that's a really wonderful talk. I hope the question addressed. And please let us thank the speaker again.
Thank you.
We are now going to have our next talk by Alexei Lisitsa from the University of Liverpool, and talking about machine learning and the large language model assisted applications of APP in mathematics.
Okay, thank you. So topic of my talk is, you can see here, and it will involve three interrelated areas. One would be topic in mathematics, then I will go to automated theorem proving, and then I will go to machine learning, and we'll see how they interact, what the opportunity are in this specific case study. And case study itself, I'm lucky enough this conjecture to be mentioned yesterday in an invited talk by Sergei Gukov, namely Andrew Skurtz's conjecture. So I will still give some preliminaries. So we are in a group theory here. We have a group presentation given by a set of generators, elements of the group, and then set of relators, R1, Rm, which are essentially words in the group alphabet, and implicitly what is stated here, they should be equal to unit in the group. So basically these words which evaluate to the unit. And okay, so this is the presentation. And then we have some transformations, which, as explained, Sergei yesterday came from topology originally. So they do make a sense in topology, but also in the group theory as well. So you can do some transformations of such presentations. You can replace any of the words by its inverse. You can take any two words, multiply them, and replace one of the components of this product. And finally, you can conjugate any word here by, again, any word W. So if you abstract away group theory topology, you can see it as a word game. So you have some words, you have some rules manipulating these words, and here we are. So what the question is to prove a conjecture or disprove a conjecture which was posed more than 60 years ago, or about 60 years ago, is the following. So if we have a presentation of a trivial group, balanced means the number of generators and relators is the same, then by using these transformations, you can always arrive to trivial presentation of trivial group. Namely, relators themselves would be just generators, letters, which then would, of course, implicitly that would equate with the unit of a group, everything would be trivial. So if a regional group was trivial, then conjecture states you can always transform it into trivial presentation. And here we have trivial example of this, almost trivial example of this type of transformation using allowed rules. Of course, presentation is very simple here to fit in one line in here. So you can apply first inverse transformation to the second relator, then you multiply and put a product instead of first relator, and here we are. We arrived at the trivial presentation of a trivial group. Generally, of course, conjecture is widely open, and it may well be false, again, as Sergei yesterday discussed in his talk. And here's the smallest potential counterexample in terms of length of this word. So nobody knows how to transform it into trivial presentation x, y, using only rules I demonstrated on a previous slides. However, if this is a conjecture, of course, there are many concrete presentations for which simplifications are unknown. So one can see it as algorithmic task, and how do you do algorithmically? Of course, one approach would be, naive approach would be by exhaustive search. You just apply everything possible, you go, and eventually, if it's simplifiable, you will hit trivial presentation. But issue here with such an approach, simplifications would be very low. Actually, super exponential size, as was shown already 10 years ago, some example, and we actually see such an example yesterday. Of course, people applied a lot of algorithmic methods. Here I mention only most prominent. And as you see here, the latest arrival was by Schechter et al., precisely a group. Sergei Gukov was involved. They applied reinforcement learning with a lot of results obtained by this application. But I would argue For alternative approach, I've been developing for at least 2018, and you can apply to the such a search generic automated reasoning. As that what is a case study, this is a very interesting task, and I would say very interesting applications of automated reasoning to mathematics. How do we do that? First of all, we would like to translate this game into logic, and we can do it in two slightly different ways, related but slightly different. We can translate it into essentially these transformations above to the statements about derivability. And again, what I mean here in the first order logic, nothing high order, nothing inductive, just first order logic derivability. And in this style, I would need some predicate P, basically as a placeholder. So if presentation holds, then it can be transformed to another presentation presented like that here. So again, by trivial transformation, you can consider the task of proving this implication, which shown here. Because this rewritability by Andrews-Curtis rules is effectively generate equivalence relation, you can equally formulate it in equational terms. But for that, you need to just a constructor f, function f, just a placeholder, and we would consider these transformations as a series of equations. So eventually, we would like to prove these things in one or two styles. But of course, to do it, we need to formulate a series, appropriate series, which would capture everything essential in this rewriting process. Of course, we are dealing with groups, so we need to have equational theory of groups to start with. But then we need just to write very natural rules. Here you see it in two styles, equational and implicational. So basically, you claim equality of a presentation xy, informally speaking, and its rewritten version rx. Rx stands for inverse of x. And similarly, you can do it in implicational style as well. So nothing fancy here. It's more or less straightforward translation as you would do, anyone would do it facing such a problem to encode it in logic. But now we are in a situation to apply automated theorem proving to this type of tasks. And here I show with just one example, the most famous example. You can actually launch your favorite first order theorem prover and put this task and try to prove it. But of course, it remains an open problem. And of course, myself spent at least some continuous running for months, for 3 months at least. Any provers with any tuning didn't help. So it's really hard problem to show sequence of transformations of this presentation to this one. Now, so now I'm finishing my first part concerning, if you like, second part, essentially what the problem is, how we can apply theorem proving to that. And what you see here is just good properties or good features of this approach. So in some sense, it's relatively complete. Anything which could be done by any other experimental approach could be actually done by automated deduction. I checked them all. But moreover, there are something which was totally new obtained in this deductive approach. And here you see the longest known concrete simplification. So effectively, it takes more than 8,000 steps. So theorem proving was able to find the sequence of simplifications which start with this presentation for Miller-Schupp family, again mentioned in yesterday's talk by Sergei Bukov. And so it took 74 days and 56 gigabytes of memory to actually arrive at the simplification. So it's quite a large proof in terms of demanding for resources. It was only possible because 2 weeks before that, I was upgraded my hardware to put 64 gigabytes. Before that, it would be just go to infinity, hitting memory bound. So 56 gigabytes. But it's still possible. But I will comment on this by the end of my talk in slightly different focus later. I will return to that. Now, topic of this workshop is, of course, about theorem proving, machine learning, especially in the age of LLMs. I would like to make 3 claims mostly they are proposals, even though I've done some initial experiments in some of them. The first one is the following. So this particular conjecture, in my opinion, is a very good playground for testing all these magic technologies in which Joseph Urban told in this morning. For example, this learning guided theorem proving could be applied here, but also I will discuss two other topics here. But first is first. Why this conjecture is good as an experimental playground? Because there are infinite families of potential counterexamples. And first two was mentioned again in yesterday's talk. And as you see, they kind of easily parameterizable families of presentations. And the last one, even more easily parameterizable Gordon family. So infinite family potential counterexamples. In each family, still there are infinitely many presentations for which simplifications are unknown. So nobody knows how to simplify them. At the same time, at least for the first two families, or not, the last two families, there are many presentations for which simplifications are known and can actually be obtained by automated deduction, automated theorem proving. So proposal here to use these data sets, generate the data sets out of these potential counterexamples, and then apply learning guided automated reasoning systems similar to Enigma mentioned this morning or any other system, and to use this for training. So that is the first proposal. Now, second, I would like to notice that the power of automated reasoning here can be seen like we replace specialized algorithms by generic automated reasoning, but there is still something to be done. We need to prepare data for this type of things, pre-processing and post-processing. And in this way, we can actually, well, the idea came, let's try to apply these modern tools, LLMs, for pre-processing and post-processing. And one particular, I would say, small success, of course, nothing as compared with the much broader applications of LLMs, but what I'm trying to do here to make something useful, and not for anybody, but just for myself. Can I actually use some of these tools for the research I'm doing? And specifically, I was able to generate Perl scripts for creating data sets for these families I mentioned on the previous slides. So effectively, you specify some parameters. So there are some numerical parameters here, but also non-numerical there. You press the button and Perl script generates the whole set of files ready to go to automated theorem proving. So that's as simple as that, but my specific satisfaction was after I was a bit disillusioned with all this LLM technology due to hallucinations and also outright false statements, but here it works perfectly, I would say. As it just produced Perl script with all, I would say, high-level industry strengths features, checking inputs, checking outputs, everything as would you get from a seasoned software development, which does this nice thing, generated data sets and from a task description. And what specifically I like, the all natural equivalencies, mathematical equivalencies. When you specify this task, you're talking about group presentations, you're talking about syntactical objects like a string of letters, and there are some assumed natural equivalencies. Like this string of letters, I can see it as a term in group theory, I can see it as a relator in the presentations, I can see it just as a string, which I specify using LaTeX conventions. All equivalence is treated correctly, and I was very happy with this particular small experience with this power of LLMs for practical tasks. And let me finish with this picture. That was my attempt to understand the behavior of these simplification sequences, again using LLMs mostly for visualization. So what you see here is a picture, LaTeX source of which was produced by LLM, ChatGPT, in about 2 hours conversation, myself with ChatGPT, given sequences of simplification steps. So I tried to make a picture. What does it show? It shows the lowest line, it shows simplification sequence symbolically of the last MS9, which I claim the longest ever produced. So 8,600 steps. But simplification sequences for similar presentations, but with smaller value of parameter n, 8, 7, 5, demonstrated somewhat merging behavior. So you see, so they do something independent for say N8 do 82 steps before it's reached some point in which it just coincides with this simplification for n equals 9. And so on. Similarly, you can see all simplifications behavior in this way, and the hope was about January 25, out of that to extract inductive argument to prove that it's simplifiable for all n. But unfortunately couldn't do it in time because in February the same year, 2025, the same brilliant team who applied reinforcement learning based on analysis of their experimental data and producing human arguments have proven by induction, so this type of things indeed simplifiable for all n greater than 3. So that's finish the story I would like to tell today, and just the final remarks. There are several statements here. First of all, automated proving is a very powerful approach to AC conjecture exploration. AC conjecture, in a way, is one of the most known conjectures in combinatorial group theory. As such, it's also a source of interesting challenging problems for ATP, which can be used also to train learning guided systems for automated theorem proving. But also, I've demonstrated with small examples that LLMs already are useful for data processing tasks related to ITP in mass. Thank you.
So you said you found this. You found this proof after several weeks or a month of running on your machine. What's your general policy for stopping these proof searches? When would you stop the proof search if you didn't find the proof in 1 month, or what was the number?
Normally, yes, but this one was, I just ran it until memory is sufficient.
Oh, okay.
But then also it happens at the time it finished, I was away at the holiday, so actually proved line for 2 weeks. So it's already existed in 2024, but I discovered it in 2025. Because I came after holidays, I found it. But yes.
So I guess the question is more general. Like, do you have at this point some feeling for how long you can run Prover 9 and still get results out of it?
Yeah, exactly at the same line. So it's kind of very difficult to formalize. I just have a feeling that somehow I get a chance. And so I would give a longer run, but it never works. And effectively, I would say concerning, for example, AK3, the famous example everybody would like to simplify. Generally, I abandoned it for many years, but then recently there revived my interest and realized that maybe resource limitations is the issue. If I wasn't able to prove it in, say, 16 gigabyte memory, maybe I would be able to prove it with 64 gigabyte memory. So again, but it's very informal argument. So it's just mainly is how many threads, non-interacting threads I can launch on my working desktop.
Oh, okay. Thank you.
Thank you very much. Let me ask you a question. Maybe you can resolve my confusion. If I understand your work correctly and the work of Sergei's correctly, these methods that you use using RL specifically try to crack some hard balanced representations that for which we don't know this path to this trivial form, basically. But that doesn't solve neither the problem like that was general conjecture was established, nor as was noticed that if you using that method in some period of time cannot establish this trivial representation for some hard example, it doesn't mean that this representation does not exist. So it's sort of my question, what's the general view that you have in terms of using AI to crack this specific problem?
You mean?
Yeah, if so far it looks like it's neither, it cannot give us as a mathematicians, it cannot give us the concrete answer either this whole conjecture is correct, or even for this specific example, which is hard example, we cannot construct as a counterexample. Yeah, this is like we cannot trivialize that. So yeah, what's the general strategy that you have in mind?
Yeah, kind of. I would say, of course, the conjecture may be false, and this simplification doesn't exist. But so much experimental work, my own and many other people, was founded because there are potential counterexamples, and provided conjecture holds true, there should be a simplification. So basically this I would put like exploration, what is possible. And of course there are these difficult cases. Of course, one can try to apply the power of formal methods to disprove conjecture. But here we go to the area of outside of first order reasoning, broadly speaking. So here is just first order reasoning. Generic first order reasoning is very useful when you have a task of infinite search. Stephan in his previous talk mentioned that we are doing search in infinite space. So that's exactly the case. So it's just using the power in hope to find simplifications. If you would like to disprove, some occasionally I think about it, but essentially you would need to find very strong invariants which prevent something rewritable into something. But this is outside of first order reasoning, at least of straightforward approaches. Not sure if, yeah, so
thank you.
Yes. So if you have any more questions, feel free to chat with our speaker in the break. So now let us thank our speaker again for the